Okay, hi everyone. Hope you're all doing well. And what I wanted to do today was cover part of the 60-second timer project that I introduced the other day in the first post. And these posts are called Timer 60 second dash 1, 2, and so on. And we'll have several of these. What I want to cover today is at least these two things here. Okay, so the part where your input clock must be one of these values, and it could be even higher. You could make it 600 or 700 hertz. But the key is that it has to be a divide by 10. So it has to be divided by 10 to drive the 163s. Okay, so the reason why we want to do that is because we want the simulation to run such that we can track the counter happening. It doesn't have to be exactly 1 second per tick of the clock. If you were to build this thing, you could do it that way just by having, say for example, a 10 hertz clock that you divided by 10 to make it a 1 hertz input that you would feed to your 163s, and then you would be able to generate a count on each one of those clocks, which would be at 1 hertz. So because we're only running in simulation, all I care is that you do a divide by 10. Okay, and then you can change your input to be whatever fits best for the simulation display. And then you must be able to pause your circuit based on a switch and then resume it where it left off. Okay, so those two things I'm going to cover today, and then I will go through some of these other things later. If we were to do this divide by 10, how could we do it? Well, we know that with our D flip-flops or our JK flip-flops, we can generate divide by any power of 2, right? We could do a divide by 2. We've looked at that by doing a feedback from on our D flip-flop, say from the Q prime or the Q bar output back into the D input. And then if whatever clock we run that with, it will be that divided by 2. And then we could feed that into another stage, and it would be then a divide by 4, and then feed that into another stage, would be a divide by 8. But they would all be powers of 2, right? So it'd be like divide by 2, 4, 8, 16, 32, 64, and so on. But I want to divide by 10 on this, okay? So it's a little bit different. You can't just line these things up, because if you were to do, say 5 of them, you're not going to get 2 times 5. You're going to get 2 to the power 5 divider, right? So it's not quite there. So we can do this with 163 counters themselves to generate that odd divider count. What I want to show is the one of the slides from this synchronous counter MSI slide deck. Okay, so that was in one of the posts. It was in this post here. Okay, this one here, MSI synchronous counters. One of these slide decks has a slide that shows a timing diagram. Okay, so we went through these timing diagrams that show the outputs for your 163 counter. These are the QDs through QA. This is the clock input. And this is that thing that we called RCO, right? Ripple carry output. And we noticed that, or we defined this RCO to be a 1 whenever the output reached its terminal count for the 163, which was all 1s. So the 1111 case, or this would be F in hex. When that reached its terminal count, which would be F, the RCO goes up by 1 for the whole time that it's an F, right? So it goes up when the count hits 1111, and that would be our QA through QD being let's see, it would be this guy here, 1 1 1 and 1, right? So when we're all 1s, the RCO goes to a 1, and then it goes back down to 0 for all the other counts. So we can use this to generate a divider of our input master clock. Okay, so how would we do that? Well, we can take and remember the counter has a load capability. We can load in any number, and one of your previous, I think the last assignment was to create a 163 counter that had a programmable load and termination, right? So it could decode some kind of terminal count, or the rollover count, I called it, and then it would roll back into the load and then load up any number, right? And we had those set up by switches. All right, well, if we wanted to divide by 10, the only thing we need to do then is we could use the RCO for a load into our 163, and then we can count backwards from there for the number of counts that we want to divide by. So, for example, if we wanted to divide by, say, 5, I would take this thing and this F, and I would go back 5 from here, right? So 1, 2, 3, 4, 5. And that's the thing I would want to load. So if I wanted to divide it by 10, what I need to do is go back 10. So if I go 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, I'm at the 6, right? So that means that if I were to use this RCO as a load, and the load on the 163 is synchronous, so it's not going to actually load the value that we put into the A through D inputs. Remember, the 163 has A through D inputs. We've got this load pin here that if we were to drop this thing to a 0, right, and it's active low because it's got the bubbles, so it's a 0, we'll load in whatever A through D is, and then you get that out on the QA through D. And when the load goes away, then you just start counting again. So I can use my RCO. I would have to invert it because it's got to be an active low signal, meaning low is when you're actually loading. And I don't want to have a low, I don't want to be loading all this time here where it's low here. I want it to be loading only during this time in here. Okay, so I just need to invert it. And that way it would be a 1 here and a 0 in here. And then what I need to do is set up my A through D inputs to be whatever I want it to load for to generate that count that is generating this RCO every n clocks, right? So if I wanted it to generate an RCO every 10 clocks, for example, I would just take my F and I'd subtract 10 from it, and I get here, or I go 10. It's actually subtracting 9 from 15 would give me 6, but it's this minus this plus 1 will give you the number that you're dividing by, right? So whatever your terminal count is, in this case it's 15, minus 6 would be 9, and then plus 1 is going to give us what the actual divider is going to be. Okay, so I then could take that signal, feed it into the load, and then every time this thing comes about, it's going to load in, and I set up my A through D to be a 6. So every time this thing comes in, then it'll load this one, and then it'll start counting again. So that just means that instead of going to 0 and go all the way to 15, which means that this RCO has a duty cycle, right, of like 1/16th, right? So because every 0 through 15, it's got 16 clocks, and then it generates, and then it'll generate again in another 16 clocks. Well, if I cut that short by feeding this into the load of the 163, I can shorten that period. And so now if I load it with a 6, then I'm going to generate that RCO. It's going to come around. When it hits F again, it'll generate that, and then it loads this back up, and then it's going to come around and generate that again. So if I ran this thing over and over again, and it just kept going through this cycle, then that would mean that this RCO is going to be having a duty cycle of 1 over 10, right? One out of 10 clocks, it's going to come up. Okay, so that will effectively do our divide by 10, right? Because I'm taking this clock here and I'm generating this signal every 10 clocks. Well, that's a divider, right? That's just going to divide this, and I generate the signal every 10 clocks. Okay, so let's take a look at a circuit that would do that. In this case here, I've got a 163. This is the 163 counter. I've got my, and let's not look at that part yet. I got this part here where I'm taking my RCO. This is my ripple carry. I'm going to invert it because remember I need it to be active low, right? So I need to take this waveform here, which is the RCO, and I need to invert it. And then I'm going to feed that back into the load pin. Okay, so that's all that's doing is whenever I have my Q through my QD through QA as being 1111, then it's going to reload whatever is on these pins here. All right, and then what we said was, well, I need to have this thing to be my terminal count, um, um, whatever I need it to be. If it needs to be 10, then I need to take that minus whatever the number needs to be here plus 1 is got to be equal to the divider number. So in other words, if I make this a 6, right, and I can see that it's 6 by looking here. This is down here, that's ground, right? So that's a 0. So I have a 0 on my A. This is my least significant bit, A. That's 0. These two are tied to VCC. So you see it, if you go way up here, there it's at VCC. Okay, so if I follow that line all the way down, that's VCC. And then that's a 1, that's a 1, and then this one here is also tied to this line here, which is ground. So 0, 1, 1, 0, right? So D is the most significant bit, that's a 0. I have a 1, 1, and then the least significant bit is a 0. And if you do 0, 1, 1, 0, that's a 6. So I've got it loading 6, I've got it counting for whatever the master clock is. And this clock here, I've got it set to 600 hertz, which will do a divide by 10 of this and generate then a 60 hertz clock. Okay, um, and that's really all you need for the divide by 10. You just need to set this thing up. So if I said I want it to be a divide by 9, what would you do? Well, you would, instead of making this a 6 on the load, uh, you could still load it on terminal, but instead of being 6, we make it a 7, right? And that would shorten it by one clock. So if I said I wanted this to be a divide by 9 instead of 10, then I could say, all right, well, what do I need to load this thing at such that I get a duty cycle on this RCO of being 9 instead of 10? Well, if I take this 7, I go 1, 2, 3, 4, 5, 6, 7, 8, 9, that will generate that RCO every 9 if I load in a 7 every time. Okay, so if I wanted it to be a 5, for example, then I just say 1, 2, 3, 4, 5. I load a B, right? 1, 2, 3, 4, 5 will generate this thing every 5 clocks. That will generate my divide by 5. Okay, so I could use this. Then this RCO is just a little square wave, and it doesn't have to be 50% duty cycle. It can just be this little blip here. As long as it's as wide as the master clock, that will generate a clock that is a divider by whatever we want it. And in this case, for 10, we just load it with 6. Okay, so that's how you do the divide. Then the other thing was, how do we stop this thing, right? So there was one of the other requirements was that you must be able to pause your circuit based on a switch, then resume it where it left off. Okay, so if I want to pause, excuse me, if I want to pause it, pardon me, I just choked on something. Okay, if I want to pause this, really all I want to do is stop the divide by 10 clock. I just want to stop that divide by 10 clock based on a switch. If I stop the clock, then everything is going to stop, right? All my other dividers are going to stop. And I haven't looked at how I'm generating the second counter yet. This is just simply for the divider, right? This is just doing the divide by 10 of the master clock. The other counters are doing the count from 00 to 59 and then back to 00, and then I'll cover that later. But this thing here, if I want to basically kill the clock to the other counters without resetting it, because you could just say, all right, well, I'm just going to go in there and clear it. Well, clearing it doesn't do it because that would just set it back to 0, right? And I said I wanted it to pause it, but then I had to kick back up where it left off, right? So resume where it left off. That means that you needed to pause the timer. Okay, well, to pause the timer, you can use the ENP control bit on this master divider counter that we have, right? So if I'm running this thing with just this master clock and I'm generating this divide by 10 through this circuitry here, I can stop it by simply making this ENP a 0, right? So if it's a 0, it's not going to count. If it's a 1, it will count. So my ENT, I tie this one to VCC right off the top. So it's always VCC here. But this one, the ENP, will also stop this counter. it won't allow it to go forward, won't allow it to count as long as it's a 0. Well, if it's a 1, it will allow it to count. So all I have to do is hook up my switch in our usual way, right? We have a switch and we have it going through a 1K resistor to VCC. So this line here is VCC. Then I'll go up to the VCC line, and then I tap off of it on the other side of the resistor, right? So this is how we normally do it, right? Sometimes this thing I put it vertically, right? So it'll be sitting here, go up to VCC, tap off the line here. So that means that when the switch is a down, it'll be a 1, I think, and if it's up, it's a 0, right? So it doesn't really matter one way or the other as long as you've got it set that you can generate a 1 or a 0. The other side of the switch just gets routed to ground, and then you can pause this thing by just connecting it directly to ENP. Okay. All right, so that's that part. That's just doing the divider by 10 and then the pausing part. Okay, so that's how that works. And I'm going to pause or stop the video here. This will be part 2 of the video series for this 60-second timer project, and we've covered these two things here. Okay, I'll talk more about this part next time, where we get it to count from 0 to 59, but let you think about that for a little bit. The thing that you basically want to be able to do is have your tens digit, right? The most significant digit, that has to only count from 0 to 5 and then roll back over to 0, right? So you have a way of doing that. We know that we can detect the output to be any number, right? We just have to have the logic in there that would detect the 5, in this case 0, 1, 0, 1, right? That's 5. And then we need the other one to detect the 9, right? Which for the ones digit. So we want this thing to go from 0 to 9, and then the tens digit to go from 0 to 5. Okay. All right. So I'll let you think about that and continue working on it. Okay. Thanks, everyone.